Good evening to everyone and welcome. My name is Adrian Smith and I'm Director of the Alan Turing Institute, and welcome to you all for tonight's lecture. If you're not familiar with the Turing Institute, we are the National Institute for Data Science and Artificial Intelligence, headquartered not far away in the British Library. And basically, we're a collaborative institute with 13 university partners and a number of other strategic partners. And we have really 4 objectives in the Institute to try and enable and develop and nurture the UK to be at the forefront of world-class research in data science and artificial intelligence. And then to do what we can to see that pulled through into making life better in various ways in terms of business and policies and people's lives. And if this stuff is really as important as we all think it is, then we need a lot more people to have awareness and skills, and so we need to be part of that agenda. And then finally, there is a public out there for whom some of this stuff is mysterious, some of it is threatening, and so we need to be involved in public discourse and dialogue, and that really is what tonight's event is about. We will hear first this evening from David Spiegelhalter give his lecture, and then we'll have a short question and answer session, and then we'll retire for refreshments and further conversation. Note that this is being recorded and will be available through our YouTube channel. There may be photographs taking place. If you're photographed and you're not supposed to be here, have a word with the photographer and get it eliminated. And if you're twittering away or following Twitter, we have one hashtag which is called Turing Lecture and another hashtag which is called Show You're Working. So without further ado, let me introduce our guest for this evening. David Spiegelhalter has been the Winton Professor for the Public Understanding of Risk at Cambridge University and is chair of the Winton Centre for Risk and Evidence Communication. He was elected Fellow of the Royal Society in 2005, awarded an OBE in 2006, and was knighted in 2014 for services to medical statistics. He has been and is currently President of the Royal Statistical Society. So without further ado, can I introduce David Spiegelhalter.
Thanks. Okay. Thank you very much indeed for the introduction, Adrian, and thank you all very much for turning up. I think it's a really mixed audience. I assume there's some statisticians, some machine learning people, some AI people, and people who are just interested, and that's just fine because I'm going to sort of be covering all that ground in a non-technical way. There's going to be some historical stuff here, which I'm not going to apologize about, because I remember a previous summer of AI, back in the 1980s when we were young. And so that was from the 1980s. There's a lot of interest in artificial intelligence and statistics. I was doing a lot of stuff on computer-aided diagnosis, then moved into evidence propagation in Bayesian networks and working with Stefan Lauritzen and Phil David, etc., and Robert Cowell on all that sort of software. And then that developed into the sort of bugs project using Bayesian graphical modeling with Markov chain Monte Carlo. And if you don't know what those things are, it doesn't matter at all. It just means that, for a long time, been involved in these kind of ideas. But over the last 10 years, I've actually sort of changed direction and gone into the sort of communication mode, making, documentaries. This was Norman Fenton, Hannah Fry, Climate Change by Numbers, Tales You Win, Science of Chance, and then doing, ludicrously populist things like appearing on Winter Wipeout, which I did rather well, but you're not going to see the video of that. I'm sorry. It is on YouTube. You can see that, and becoming bizarrely world champion at Loop, which is a version of billiards played with an elliptical table and a single pocket. It's like a putting green, but with some maths, you can do quite well. Okay, so what I've done now, what I'm really interested in now is in communication. I'm philanthropically funded by David Harding and Claudia Harding of Winton Capital, a hedge fund, who support this whole gang now, Winton Centre for Risk and Evidence Communication, who are psychologists, ex-BBC communication people, web designers, who are concerned about getting mathematical, statistical, algorithmic ideas out there into the population in a, well, I think, actually in an ethical way. Ethics drives our program because we're concerned with providing people with information. We're not trying to change behavior. We're not trying to sell anything. We're not trying to manipulate anybody. We're just concerned with providing information. And that's one of the aspects I want to talk about this evening. Okay, so summary. What I'm going to talk about is trust. You know, the usual stuff. Structure for evaluation, ranking. I'm going to do a little bit of technical stuff on ranking algorithms because I think it's fascinating, the competitive aspect of algorithms. Layered explanations, ideas of that, explaining regression models, communicating uncertainty, and finally how some fairly basic, throughout, statistical science might help in these issues. So I'm going to do explanation, all that sort of stuff. It's the things that are, you know, important topics at the moment. I'm going to talk quite a lot about medical systems, and I can only scrape the surface, but I hope things are more general than that. Okay. If you're going to talk about trust, you have to talk, use this lady, Baroness Onora O'Neill, who did the Reith lectures on trust, and it was quite extraordinary. I mean, she is very good indeed. And so she's going to come up a couple of times in the talk on trust, and many of you will know this. The big thing she says is that we as sort of developers or professionals should not be trying to increase trust. We should not be trying to get people to trust us. That's putting the wrong thing first. What we should be doing is trying to demonstrate trustworthiness, because that is within our control. And she's had a lot of influence. The new code of practice of government statistics has got 3 pillars, and trustworthiness of statistics is the #1 pillar for government official statistics now. And that is when, so I'm going to be pushing throughout all the time about trustworthiness. And this is, we see a lot of stories about AI and its potential, blah blah blah. We expect all these we get these headlines all the time. I just picked on some, particularly local London medical ones, but the papers are full of them all the time about what AI and machine learning is going to do to us. And my running theme throughout this is that we, as consumers, should expect trustworthy claims. And 2 sorts of trustworthy claims, and I think it's really important to distinguish them. The first is that the system should be making trustworthy claims. When it's making a diagnosis, when it's giving a probability, when it's making anything, what it says should be trustworthy. If you've got an algorithm that's coming up with a conclusion, whether it's about a loan, whether it's about anything, it should be trustworthy. Okay, secondly, trustworthy claims should be made about the system, by the developers, by the company, by whoever's in charge of it, responsible for it. So those 2 things, and they're connected, but I think they're good to keep them separate, because one is about what the system does itself, and the other is what is claimed about it. And they're both really important, and that's what I'm going to be emphasizing. So when we're talking about trustworthy claims about the system, we're really talking about how good it is. Actually, is it any good? Are we boasting, or have we got realistic claims? There's a hugely established structure for making trustworthy claims about medical pharmaceuticals and increasingly about medical devices. That's been around for ages. There it is. It's very simple. Everyone who works in medical statistics knows this off by heart. Been around for decades. Everyone works in this context. And I think it's extremely valuable because it's provided a structured way for making trustworthy claims about drugs. Phase 1 is when you're just testing on healthy volunteers to see whether it's safe in that. Phase 2 is proof of concept, where you're trying to estimate efficacy. Again, on people with the disease, highly selected subjects try to work out optimum dosage for perhaps. Phase 3 is the important bit where you're actually putting into practice, doing randomized trials to see whether it actually has benefit over the standard treatment. After that, 2 successful studies, you might be able to get it then approved by regulators, get it sold, and then you have to go on to phase 4, which is post-marketing surveillance. So that sort of structure has been around for ages. What I think is necessary, and has been proposed by a number of people, myself included years ago, but others as well, is a similar structure when we're talking about algorithms that are making claims. And not just medical ones either, but particularly for medical ones. That the phase 1, the digital testing, just how accurate is it on your database, on your test set, is only the very, very first phase of that stuff. That's just digital testing. Laboratory testing is when you're still not putting it out, but you're starting to compare its performance with experts, perhaps, to look at how does it match up to what you'd want it to do. The phase 3, the controlled trials of impact, as far as I know, almost never take place, which is actually what is its incremental benefit over what's done at the moment. Because you can't just assume that it's going to be a benefit. It might actually have harms associated with it. And phase 4 is monitoring for problems. So I think it's incredibly important to have a structure like that. And whenever I hear a report like the ones I put out, I thought, well, what phase is this at? And usually it's 1 or possibly a little bit of 2. So I'll just try to whip through some of those issues about the phase 1 digital testing. Now, I can't resist doing this because this is a statistical perspective on algorithm competition. Do people know about Kaggle? Who knows about Kaggle? Okay, yeah, good. Kaggle is an online competition system where there's a data set which has been split into a training set and a test set, and people, they give you a set of data, and you can design your algorithm and submit it, and there's a leaderboard which is based on part of the test set, but then finally at a certain date, then these algorithms are tested on this hidden test set, and a winner is announced. So I'd like to put a perspective on those. I come from North Devon. I got a little flat in Ilfracombe, beautiful place for holidays. I do recommend it enormously. And in North Devon graveyard, there's a gravestone. In Ilfracombe graveyard, there's a gravestone, which is a curious gravestone, and it's to Francis William Somerton. Of course, it's not his actual grave because he died on the Titanic in April 1912, aged 30. So those of you who know Kaggle know what's coming next, is that I'm going to look at predicting survival, who survives the Titanic, which is a classic problem. So there's the Titanic. Actually, look at that picture quite carefully. Look at him. So we'll come back to him later. A quick plug. The reason I'm doing this, because it's a popular thing to do, and I've gone into a book that's coming out next year. And I got a lot of help from Maria Skularidou to do this programming. And there's a lovely database which Kaggle have been using, which you can download freely, the whole database of 1,300 passengers on the Titanic. What happened to their sex, their age, how many siblings they had, what their ticket number was, how much they paid for their fare. In decimal, this is £8, 1 shilling. This is Southampton or Cherbourg, and crucially, what class they were and whether they survived or not. So these all died. So there he is, Francis William Somerton, who died. Okay, so the issue is, this is on Kaggle at the moment. There's been 59,000 entries into this competition for trying to predict who survives from all this data about the cabin and the tickets and things like that. So what I did was take this database of 1,300 passengers, split it into 70% training set, 30% test set, and reproduce the Kaggle competition. I didn't do the actual Kaggle. All the data's out there, so you can in fact cheat. Now, I'm not suggesting that some of the people in the Kaggle competition are cheating, but some of them are claiming 100% accuracy. Oh, yeah, likely. Okay. So which is the best algorithm to predict who survives? And what I did was just, with Maria's help, just run through R-caret. There's a function where there's a load of machine learning algorithms which you can apply without any great knowledge. And the first thing I should say is this is not optimized. There's no great effort to develop the features. There's a little bit of coding in terms of the titles, perhaps. And there's tenfold cross-validation in the training set, but these are not hugely optimized algorithms. But there's a whole lot of algorithms, and their accuracy and their mean squared error, known as the Breyer score. And what I mean by mean squared error is counting as 1 if they survive and 0 otherwise. And what you do is each of these algorithms can give a probability that they survive, and you look at the difference between the probability and what happened and square that. And that's the mean squared error. And it's also known as the Breyer score from the weather forecasting, where this idea was developed. Okay, what do we see? The simple classification tree was best, but see average neural network second, blah, 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 logistic regression, random forest, some of these, this is just telling everyone's got 39% chance of surviving, didn't do very well. Okay, so this is the kind of algorithm that actually won, simple classification tree. Very simple about whether you're third class, how big the family is, have you got an odd title, but crucially, France's title, Mr. Yes, plonk, you're going to die. Well, that's it. So that was pretty easy. It's not a very simple algorithm, 16% chance of death. And this algorithm does incredibly well. It does very well indeed. Okay, so that's the Breyer scores of all these methods lined up. Now, the point is, though, that's the best. This is the worst, clearly the worst. Well, actually, is there any difference between these? Nobody does that in Kaggle. They just produce some ranking without saying, well, actually, this is just luck. There's only test sets, only 400 cases. There's a lot of random variability. And I can put a standard error on each of these, and they look incredibly similar. However, that would be a really stupid thing to do. It's the wrong thing to do. So you see, these all look very similar indeed. But what it's not taking into account is that these are all being done on the same cases. So you should not just look at the standard errors. These are not independent. If they're done on the same cases. So you should always just look at the difference between algorithms. You look at the difference on each case, and it's the difference that is the thing you should be analyzing. So that's potentially a very misleading graphic. If you calculate the differences with the simplest method and do the standard error of the differences, you can see that the first 4 down to the logistic are not significantly different, actually down to random forest. But after that, these, for example, support vector machine and complex classification trees. Yeah, they're significantly worse. And you'd have missed that completely if you just looked at the standard error of the thing. So this is like, you can do a paired t-test. It's as simple as that. So it's an absolutely crucial thing to do. Okay, now, but the other thing, so these look like, well, does it matter? Actually, look, maybe the neural network is the best. What can we do? Because just because someone's the best in this league table doesn't mean they're the best algorithm. Just because a team wins the league in a football doesn't mean it's the best. And there have been a whole lot of methods, again from statistics, on ranking institutions, hospital, football teams. That just means to get a probability of the rank, the probability that they're the best. Lots of methods. I think the easiest one for this one, how confident, for example, can we be that this is the best algorithm, is to do a simple bootstrap. A bootstrap is when you take the 400 test cases and resample another 400 from it with replacement. So you'll get something that looks vaguely the same, but a bit different. There'll be some multiples of the same cases and things like that. So you do that, and then you pretend that's the test set and rank all those algorithms. And this time they make flipped positions. Sometimes this one, it may do better on this test set. Do it again and again, thousands of times. Though, a quick note though, this is to rank the actual algorithm, the fixed algorithm. If you want to rank the method, it's a lot more complex because you've got to bootstrap essentially the training set as well. Okay, but what you get then is a really cool thing, which is the probability distribution over the true rank of these algorithms. So the cart, that's not bad. It's about 66, hang on, where are we? Yeah, about a 63% chance this is the best, but about a 23% chance the neural network is best. And then actually the random forest, which was 5th in the league table, 8% chance is actually the best algorithm in terms of mean squared error. So, the simple ranking of algorithms, you've got to be really careful about it. You've got to be a lot more sophisticated than it can be done. And it's just using some very basic statistical tricks to deal with that. Now, okay, who was the luckiest person on the Titanic? This is a ridiculous thing. Him. He was the luckiest person on the Titanic, I would claim. This is Carl Dahle, 45-year-old Norwegian, travelling on his own, paid £8 1 shilling, the same as Francis Somerton. And he got the lowest, the highest Brier score average over all those algorithms of anybody else. He was the most surprised. He should have died, but he didn't. So he's a really surprising survivor. And you can look him up on the database. Now, it turned out he dived into the water, so he was floundering around in the water and got into a lifeboat. They didn't want to have him in the lifeboat. So, there he is trying to climb in, and they were trying to knock him out again. But he fought his way on. So that was cool. So he survived and went on to marry, and that's his wedding picture and things like that. And poor old Francis Somerton didn't, and his wife was left with just £5 in Ilfracombe, less than Francis spent on his ticket. Okay, so that's just some of the statistical insights we can get from that simple digital testing, all that stuff that's done in competitions, machine learning competitions all the time. Laboratory testing. Now that we're talking about whether the thing is actually any good or not in practice, but compared with other people. And Alan Turing, who we're going to come to twice, had this idea of a Turing test in 1950 when he wanted to compare a computer and a human. And this is where they sat behind a curtain and another observer could interrogate both and had to guess which was the computer. So that's the idea of this imitation game and the Turing test. The modern version of that people do in terms of algorithms is to, for example, put together a team of doctors of various sorts and with the computer. So these are the judges. These are the people doing the assessments. And they get presented with a whole lot of test cases and judgments, and then their judgments are presented in a unified way, randomized, blinded, so you don't know which is the computer, and then some judges come along and decide how good those assessments are by these initial set. And essentially, they don't try to guess which the computer is, but they want to see whether the computer is in the middle of the rest of them. And those have been done for some time. They actually were done, originally in the 1970s, back with mycin, which is an old rule-based system for antibiotics. And one of the issues of when this happens is that suddenly it's revealed how the doctors, there's no gold standard. The doctors don't agree either. So they disagree with their colleagues as much as they disagree with the computer. In this case, over 30% of the judgments, the assessments being made, were judged to be unacceptable, whether it's made by a colleague or whether it's made by a computer. So this can reveal all sorts of stuff with doctors. This has just been happening. Babylon AI, which you'll have heard about, is a system with a chatbot and a way of to put you in touch with a GP who talks to you over the over the web, can actually examine you physically, well, from a distance anyway, and has got a very nice natural language processing algorithm for suggesting the next questions to be asked by the doctor, and it's it looks really cool. Okay, but is it any good? Comes up with a probability, a diagnosis, and a short list with probabilities attached to them. Is it any good? So this sort of claim is being made by Babylon by using one of these Turing Test type things. They got together a panel of doctors and the computer, and then got an external judge to decide how the computer was. And the computer was sort of in the middle of the doctors, essentially. And for some of them was better than them. But that's been critiqued. There's a recent paper, a letter in the Lancet, just last month, that criticised this study, this attempt at a phase 2 study. Said they were very good to do it, and really said the software was good, but essentially saying this was not statistically rigorous, very rigorous. There's no significance testing, there was no analysis, etc., etc. So I think Babylon is to be congratulated for actually carrying out these studies, but actually, if they're going to be taken seriously, they've got to be done rigorously. We've got to really think about these things and take them seriously indeed. What this group did say is that the crucial thing that was needed was further evaluation, in particular, this idea of a phase 3 study. What does Babylon add to what would otherwise happen, etc. And this seems to be really crucial to get onto field testing. And this is where, which just doesn't happen very much at all. Partly because I think, actually designing a phase 3 randomized trial of an algorithm is quite tricky. One element of it, you might think, we'll just do a simple randomized trial and have, a whole lot of patients coming up, and they're randomized to whether the algorithm's used on them or not. But usually, that's done mediated by a doctor. And the doctor's going to learn from the algorithm. So he's going to start applying what he's learned on the cases when he didn't get it to the cases where he did, or the cases where he did get it, to the cases where he doesn't have it. A lot of potential for contamination. And this leads to the idea of cluster randomized trials where the doctor is randomized, some get the algorithm, some don't. And these have been, cluster randomized trials are incredibly established for changes in medical practice. When you expect a strong group effect, you've got to be careful with the analysis, but it's an absolute standard design. The other design that is popular when you're introducing new technology is a stepped wedge design. And that's where essentially you do a randomized rollout. So you want to introduce the thing into 7 centers over a period of 14 months. So what you do is monitor all of them for the first 2 months, and then pick one at random and put it in there for 2 months. But keep on monitoring the rest. And then pick another one at random and put it in there after 2 months, etc., etc. And so you can get contemporary controls all the time. It is randomized. It's a powerful design used extensively in rolling out vaccine programs, etc. And we're using this one. We're using this one when we're rolling out an algorithm, which I'm going to talk a bit about later, to all the centres doing transplants in the country, doing lung transplants to start with, and we're randomizing the order in which they're going to get it. So it's a powerful design. I'd like to talk about an actual cluster randomized design of a diagnostic system for diagnosing acute abdominal pain. This was where 40 junior doctors in a large hospital in A&E were cluster randomized so that 12 were just controls, 12 filled in the forms, 8 did the forms in the computer, and 8 did forms in the computer and got feedback on their performance. Now, the issue about this is that, you know, it was a big study. You know, it was a naive Bayes algorithm, 5,000 patients, but it was very clumsy to use, and that's because it was in 1983 with a Commodore. And it was awful. It was awful. They had to sort of fill in a form and then give it to an assistant who went over the corner and tapped this thing in and then got the printout and went back to the doctor. So they didn't use it very much. And it wasn't very good anyway. It's a pretty useless algorithm. It wasn't very accurate. It was overconfident. They didn't use it very much. And it very rarely actually corrected an initial incorrect diagnosis. But what they were encouraged to do was fill out the form and make an initial diagnosis. They were encouraged to do that. So this rubbish algorithm on a rubbish old bit of technology actually helped. There was a significant reduction in admissions and surgery of cases that didn't need to be admitted in surgery, didn't have an organic cause to their illness. They didn't have appendicitis or pancreatitis and things like that. So this was beneficial. This absolute rubbish system was beneficial. Okay, so why did it have a positive impact? Well, you know, it was all explained by the fact that that fewer people with this non-specific abdominal pain were admitted and then went on to operation. These unnecessary operations that were taking place were halved. Basically, they were making more correct initial diagnoses, and the crucial thing, it was a cultural change, which encouraged them to, by filling in the forms, even when they weren't filling in the forms, to make an initial diagnosis, to have the confidence to say this is not an organic cause, instead of just passing it on, oh, well, we'll just admit them. Very powerful impact through a useless algorithm. So I think you don't find this stuff out until you put it into practice. And it might have been harmful. This thing could have caused harm. These are not self-evidently beneficial. So, you know, it's an old example, but I still think it's got some value. Oh, in phase 4, I just don't want to go on this in detail, but except to say there's a really good paper in Journal of the American Medical Association by Ted Shortlift, the same Ted Shortlift who was doing the mice and experiments in the 1970s, for heaven's sakes, talking about the importance of keeping systems up to date when they're in practice. They've got to be fail-safe, near misses or other problems. You can't just leave them alone. Things change. You've got to keep them up to date. So we won't talk about that one. Okay, that's, I'm going to have a quick drink. Oh, yeah. Ooh, Any questions? Any questions? Go on, let's have a little pause. We'll have a drink. Any questions? Otherwise, I'm just going to carry on regardless. Okay, off I go. You'll get plenty of time for questions afterwards. Now we come to this whole crucial thing. I've talked about evaluation and the need for trustworthy claims based on rigorous evaluation. Transparency. Everyone says, it's got to be transparent. It's got to be transparent. Onora O'Neill on transparency. She is so clever. She is brilliant. She's studied Kant for 50 years and you just think and comes up with how bad transparency is. That transparency is just a means to an end. It's not an end. It's not an end in itself. Because disclosure is not helpful. Just going blah and putting your code out or something like that, for heaven's sakes, who's going to understand that? So she's made this really nice summary of what she calls intelligent transparency or intelligent openness. Royal Society publication on open data is very clear on this and says that if you're going to be transparent, if you're going to claim that your system is explainable or transparent, it's got to satisfy 4 criteria. Really good to remember this. It's got to be accessible. People have got to be able to get at the information. And this is any information, but certainly about an algorithm. They've got to understand it. It's no good just baffling them with maths. It's got to be usable for whatever they want it for. And that means different sorts of people. You know, so this might vary definitely in terms of the audience. There's no single usability criteria, no single understandability criteria. So this applies differently for different types of audiences. But it's got to suit people's needs. It's got to satisfy their needs. And then finally, this is the real cracker. It's got to be accessible. See, this is where the title of my talk comes from. If necessary, someone has to be able to check you're working. Now, not everyone will. For heaven's sakes, nobody wants to do this all the time. Most people just want to trust the algorithm. Yeah. In fact, of course, it can lead to overtrust in algorithms, which I'm sure we'll come on to, the idea of overtrust. But if necessary, somebody, if they want to, has to be able to check the work. That's the crucial thing. Okay, so Other people are endlessly coming up with lists of similar things when it comes to algorithms. There's lots of lists like this about accountability and whatever. This is the one I quite like, the ones from FATML, which is fairness, accountability, and transparency in machine learning. Principles for accountable algorithms. They've got a nice list here. Why I like this list is that transparency is not on the list. So they have come to the same conclusions as Onora O'Neill, that transparency is just a means to an end. It's not an end in itself. You have to think beyond that. So they've talked about responsibility. When this thing goes wrong, who takes the hit? Who do you go to? Auditability. Now this is the accessibility. Somebody has to be able to check it. The accuracy, and that's to do with the trustworthiness of the claims made by explainability. Can you get it? And fairness. So I'm going to talk a bit about the last three of those. A little bit about accuracy, explainability, and fairness. Okay. So what's not there is interesting. Is it actually does it work? I'm surprised in the social impact statement. It shows what is the impact? Actually, is there any benefit? What are the benefits and harms of this thing? Again, you can't take it for granted that this wonderful bit of tech is necessarily going to be a good thing, even if it's been a good thing in your lab. Okay, transparency does not necessarily imply interpretability. Lots of people have been saying this. And here's just a simple example. That's a classification tree I grew for the Titanic. It's not bad. It's completely transparent. It's totally incomprehensible. I mean, you can follow a path, but you try to explain that to anyone, and yet it's totally transparent. It's very easy, but actually it is not. It's not interpretable. It's really bizarre. I can't work it out myself what it's doing, really, why it's doing it. So this is important, and there's a distinction people make between global explainability, which I quite like. That's about the algorithm in general. So here's just a whole lot of points, and because lots of people have made this stuff, so this is not really original. They sort of said, so this is not about specific cases. This is about the trustworthiness of the algorithm in general. Where does it come from? Is the training set representable? Can I understand it? What's in general the most influential bits? What are the evaluations of it, etc. And there's lots of checklists that can be should be adapted that have been also for publication of evaluation studies. There's checklists out there already that have been developed for medical informatics that could be easily adapted for algorithms. So this is, again, if we want to have trustworthy evaluations. Now, I think that this is the interesting one, which is the local explainability. When a judgment has been made, when the computer has said no, and you want to say why, or the computer has said, sorry, you're going to have 6 years in jail, you might say, well, why? I'm not going to go into, I could talk about lots of these in real detail. What drove this conclusion, Lime is a lovely thing that some of these work for black boxes. Lime is a black box, a way in which you take something that's come out of a black box. You can't see why it came up with this conclusion, but what you do is look for what it would have said about cases nearby, and then fit a sort of local linear model, and you can see what the sort of local influences of each of the individual features that are going into the conclusion is. So it's really, I think it's very nice. This is one of the important ones, I think. What if there's been different? I don't know, when you get insurance online, I do hope you'll lie and start clicking different things, saying, what if I lived in this street instead? Or what if I was younger? Just to find out what's driving the algorithm. So that's really important to do it. What tipped the balance? I won't go into that. I could talk about that for ages, et cetera, et cetera. One bit of explanation, I mentioned black boxes, and I'm going to come back to that in a moment, because the thing is a lot of statisticians would say, oh, well, nice regressions, you can explain them. Big black boxes, deep learning, you haven't got a chance. People are making a real effort, and I'd like to really point to the application here with you may have heard of this Google DeepMind with Moorfields Eye Hospital, recent paper in Nature Medicine, clinically applicable deep learning for diagnosis and referral. And they were really conscious of the fact that they were taking a 3D, original image of the eye and ending up, the algorithm, deep learning algorithm through layer after layer after layer, finally came up with a probability of diagnosis and a probability of what should be done with this patient. 99% urgent it should be, because this is the diagnosis. Okay, so it was just doing the whole thing. But for explanation, they've managed to separate, to look at some of the intermediate steps, but look at what they call these segmentation maps. I haven't got a clue what it actually means, of course. But this is, because this has been, I think, it seems to be very strong collaboration with the clinicians, that the clinicians felt would explain why at the intermediate steps of what were being made by the algorithm to come to these conclusions. So this is a really neat example, I think, of trying to make a black box more explainable. I'd like to talk about one we've developed. I won't try to go online and demonstrate it, but this is Predict for women with breast cancer, and this is the front end. You can just go on, you go onto NHS Predict, and you'll get onto this. Make sure you get onto version 2.1, which is the one we've put the front end on. So our Winton Centre has been working with other people on the people who developed this algorithm, and it's basically the idea that this program works both for patients and professionals, so that it can be used by the doctors in their multidisciplinary team meetings, and then can be used to explain things to the patients. And it can be used actually by the patients themselves and support groups if they want to. And we've done a huge number of interviews with patients and doctors and things like that, and found out we could use the same interface for both, with as long as there's a lot of help and explanation built in. It provides personalized survival estimates out to 15 years. It's based on a statistical model, a competing risks in Cox model, based on nearly 4,000 women, validated in 3 independent test sets. A new version is being developed. Extensive iterative, that's why we've got psychologists working on this stuff, user-centered design. And amazingly, it's being used by more than 30,000 on 30,000 cases a month around the world, about half in North America, half in UK and Australia, and all other countries besides. And it's being used in more and more and more. Okay, we're starting a phase 3 trial in which we supply side effect information, because we want to. It's already been in use, that's the trouble, for some time, the original algorithm. So actually trying to work out the benefit of the algorithm is quite tricky. We're doing a more basic one for other algorithms we're introducing, because we're launching one for prostate cancer and one for kidney, heart and lung transplants using fantastic data from NHS Blood and Transplant. Okay, so basically it's an algorithm, it's where you put in your clinical features of the tumour and the woman's age, and these are the treatment options, and this is for the doctors. It comes up, and you can do this on your mobile phone, it'll come up with what you'd expect the 15-year survival for this woman, all-cause survival, be 46% with surgery alone, but it would go up to, you get an extra 8% with hormones, another 7% chemotherapy, 4% for trastuzumab, that's Herceptin, 2% for biphosphonates. So you get up to 67%. And that's the sort of thing that the doctors want when they're trying to decide whether to, what treatment to recommend. For example, if this is only 3%, they're very unwilling to give chemotherapy, because it would mean, for example, that they would have to give chemotherapy to 30 women just to get one extra 15-year survivor. And that's not very good. The crucial thing is that, and you may notice along here, is that we're trying to explain these complex results in many different ways. One size does not fit all. That was, the doctors like just the table, but here's a picture. Here's a survival curve. People can understand survival curves, and there's lots of help, information, and extra things to click, and nice coloring. This is the innovation we got here. This is the thing, this is the curve, the survival of this woman, the expected survival, or women like her, if they're actually cured. Because this is as good as you can get. If we could cure her cancer, she'd get up as far as that. And of course, for much older women, this comes down quite strongly. So that sort of puts it in perspective a lot. We can do it as a bar chart. Again, being tested on individuals. It used to be more complicated. It looks quite complicated, but actually with information, nice information buttons, you can understand it. As a saying, what does it mean for 100 women? Similar women. So in sort of text, and then the icon, the standard old icon array. This is the only sheet where the word death is used. Otherwise, it's all in terms of positive framing of survival. It's the only one where death is used. We're amazed that patients actually like this image. We didn't think they would. They didn't like it when these were little people, little women, and these were dark black. No. Well, we very quickly found out that was a very, very bad design choice. That was not on at all. And I mean, I can't demonstrate it now, but if you go on and you change the details, these just change instantaneously. You can do incredibly quick counterfactuals. What if I didn't take this treatment? What if I were a bit old? What if my tumor were a bit smaller? What if blah, blah, blah? And it get an instant response, which is hugely beneficial. So there's a form of explanation in different forms. We can put uncertainty, for those who really want it, on the benefits. You can get some confidence intervals on the benefits. Basically, you get a verbal gist. You get multiple graphical and numerical representations. There are then texts and tables you can find showing the methods and the coefficients of the thing. You can get a PDF of the maths if you really want, and you can download the code from GitHub. So you can do the lot if you want it, for very different audiences. And then within each of these layers, you've got multiple representations. So this is trying to fit to what the demands of many different audiences. So, if you want to, you can download all that lot. Nobody has yet, except, can't see why. I wrote all of that, put it up there. Nobody wants to see it. It's really disappointing. What a shame. Okay, so explainability and interpretability is important, but there's lots of different audiences. I won't go into the legal aspects of GDPR about whether actually this seems to be contested about how much explanation is legally warranted. It needs to be properly evaluated. It could cause trouble. We don't know whether, if we start telling women about side effects, it actually might, if we do it in the wrong way, and badly, and over-emotionally, we could cause more trouble than it's worth. So we've got to be careful. There's all sorts of clever stuff going on with explaining black boxes, and the DeepMind one was an example I showed about how to do that. But there is this big, the statisticians come in and say, well, why are you building this black box in the first place? Why not build a model you can interpret? Why, can't we just use simpler models, like the Titanic? Why do we have to have a complex model? Couldn't we have something simple? And this is really, comes up when algorithms are proprietary, and you can't even see them. So this was I think this is a pretty well described. Oh God, I'm being filmed. I better not say too much. Anyway, I don't think this is an extremely good practice. This is Compass, which many of you have heard of, which is a proprietary US algorithm for predicting recidivism. It's used for bail decisions and sentencing decisions in many US states. You get lots of information. It generates a 1 to 10 score. Who knows how? It's proprietary. Nobody has any idea how those systems are weighted, what's done with them. It's been accused of racial bias, but I think they actually have contested that quite reasonably. It's been appealed against because the guy said, why have I been sentenced to 6 years? Loomis got sentenced for 6 years. Why? He couldn't tell him. But the court issued warnings saying, they weren't very happy about it. But recently, a paper's just come out this year that absolutely hammers it. It says that you could do online, completely unskilled people made their judgments were just as good as Compass. Like wisdom of crowds. I just asked people and they were just as good. And you could match it just as well by a simple regression model with 2 predictors, age and total previous. So all this sort of smoke and mirrors of this magic secret algorithm is commercially proprietary. You could replace it by a simpler equation. And lots of people have looked at this now. This is work by Cynthia Rudin, showing these very incredibly simple scoring systems can do as well as Compass, just by adding up points, totally transparent. Everyone can see exactly what's going on. So I think there's a real danger of, actually sort of the complexity hiding a lack of performance, and everybody who's fitting a complex model, I'd say, can you do something simpler? Can you see? So she would claim that you don't need to train off performance against interpretability. You should be able to find an interpretable model that does as well. And I mean, that's a big challenge because that's not. I'm not sure about that working everywhere, but it's certainly worth trying to see if it works. Okay, just to go back to Alan Turing again. He had an approach to explanation, really cool. In the Second World War, when he was, in Bletchley Park. They were using naive Bayes classifiers. No, I won't go into the details of this, but essentially, these are the systems they were using. They took logarithms. They essentially ended up using a scoring system where they had these things called weights of evidence. And the weights of evidence were these log likelihood ratios, which are just the probability of the setting that they'd found, the particular signal they'd found, given one setting, compared with the probability of that signal given another setting. And so it gave support for or against 2 particular settings. And this was promoted by Jack Good in the 1950s. The crucial thing about this is that it's a number that's rigorous, but it also provides an explanation because you get positive and negative numbers depending on whether it's for or against the hypothesis. A bit like Cynthia Rudin's scores there, you've got -1 or +1. It gives an enormously sort of sudden, you get explanation. So we had a system years ago for diagnosing gastrointestinal problems, which, for example, for this patient, we could give evidence for peptic ulcer, a whole lot of scores for different things that the patient reported, and then evidence against peptic ulcer for other things that they reported. You get evidence for, evidence against, take the difference, and turn it into a probability, a rigorous probability. So I think, as far as I can see, Babylon is a Bayesian system that produces a probability. It could be doing this. You know, these are really simple ideas. It's just balance sheets of evidence for and against, which I think are extremely powerful for explanation. Okay, communicating uncertainty. How long have I got? I must be coming soon. Okay, a bit longer. Okay, not too bad. Yes. Again, getting back to FATML, they got a nice statement about, you know, if the system is going to be making trustworthy claims, it should say when it's uncertain. It should say when it doesn't know. And when it says it doesn't know, it's got to mean that. I don't know. Yeah, you know, I rely on, you know, what I call Mrs. Google when I'm driving abroad. And I was, you know, driving in Portugal, and she was great. She was telling me everything. She did try to take me down some steps at one point, which wasn't great. And but twice she did things where she actually told me to turn left when it was right, confidently. But once, I don't know if anyone's had this before from Google Maps. She actually said, "I'm sorry, I cannot help you." She got lost. It was wonderful. But at least she said she didn't know. She said, your guess is as good as mine, essentially. It was slight panicking. I was in the, you know, middle of a Lisbon suburb, but never mind. She got a grip and got me back on time. But I admired that honesty of saying I don't know, rather than confidently taking me down the steps. Okay, it's part of being trustworthy to communicate uncertainty. But will acknowledging uncertainty lose trust and credibility? This is one of the issues. So probabilities should be well calibrated. This is the first thing. If a system's going to give up, you know, Google DeepMind was giving 99% probabilities on its diagnosis there. Well, actually, was it right 99% of the time it said that? That's really important, that those probabilities mean what they say. The Titanic one, when it gives a probability, the observed event percentage, you know, it's on the line. You know, my little classification tree was well calibrated. So, and there's actually a really simple way you can just test for the calibration of any probabilities coming out of a system. So there's a bit of maths. Come on, you've got to have maths. Simple, yeah, look, isn't that nice? A little bit of maths. Okay, here we go. Simple test for calibration. X equals 1 if event occurs, X equals 0 otherwise. Pi is the probability given to the event occurring. So the mean squared error is just the average of the squares of the errors. That's it. So that's the formula for the mean Brier score. Now, you can multiply this out, and since xi squared equals xi, because it's a binary variable, you can rewrite the mean Brier score in this form. This is a beautiful decomposition of the mean Brier score into two components. This measures how uncalibrated the probabilities are, how far the x's actually are away from the pi's, and this just measures a separation, how split the probabilities are. In other words, are they all saying the same thing, or are they nicely different? That's the discrimination. So nice two components. Now, if I take the expectation under the null hypothesis that this is perfectly calibrated, that means the expectation for each of these is pi, and the variance is pi times 1 minus pi. So simple binary thing. In other words, if xi really is, you know, a quantity with probability pi. And when I do that, I can find out the expectation, the variance of this mean Brier score, and that's the sum, that's the variance. And so I can produce a test statistic, a sort of t-test. And this simple way, and it just give me a global test for calibration. This is used, this got about 300 citations, and it's used a lot in prognostic index stuff. And it seems it's incredibly easy to use on algorithms. So for example, when I compare all these algorithms, this is what I'd expected the Brier score to be, given the probabilities that are being announced. And these are pretty good, but the random forest is rubbish, and so is the nearest neighbor. They're grossly overconfident. Its probabilities are far too near 0 and 1. It's giving lots of really extreme probabilities, and that's not being justified by the events that are happening. So a very simple idea, and this, you could just do this from a t-test or something like that, but a very simple idea of quickly identifying which algorithms are just being overconfident, and that's a dangerous thing. Now, uncertainty, I'd argue, is really important, and here's a little example. You might have seen me use this before. is more statistics than machine learning, but I'll come back to that, I think, why this is relevant. So let's say, look, back in January, UK unemployment fell by 3,000. Is that a trustworthy number? Come from the Office of National Statistics, reported by the BBC. Surely we believe that. Must be trustworthy. So we go onto the website, and we click down, and we find quality and methodology, and we click on, and we find out that this has got a 95% confidence interval of plus or minus 77,000. Yeah, so maybe it's not that trustworthy. Maybe they haven't got a clue whether unemployment has gone up or gone down, and that would be the honest response. We have not got a clue whether unemployment has gone up or gone down. Somehow journalists can't bring themselves to write that. I don't know why. Anyway, so that is not, I don't think, trustworthy reporting. Can we do better? Bank of England does fantastically better. When it's making projections, it uses this fan chart. These are 30, 60, 90% intervals, but also in the past. It's clear that, they're really uncertain about what's going to happen. They're pretty uncertain about what's happening at the moment, and they haven't got much of a clue about what happened in the past. So they're really honest, really upfront about their uncertainty there. Can we use that? Can we broaden out those ideas? We're working with the people. We thought we'd work in an area that wasn't contested. There's a sort of safe, uncontroversial area. So we're working with the people at the ONS who produce the migration statistics. And because we don't know how many migrants there are, it's based on not a very good survey, et cetera, et cetera. So in the last report, November, that's how the lines are reported, using these kind of fuzzy fans. Now, and to show that these are 90, 60, and 30% intervals with a little bit of fuzz drawn on them in a slightly artistic way. We're doing experiments, randomized experiments with online panels. People like this stuff. They can understand it. We compare it with error bars, because I much prefer this to a simple error bar, because that brings the eye to the most extreme values. But we got a note, and people have pointed this out. This is only for the known uncertainty for the survey estimate. And it doesn't deal with the non-sampling errors. There still is verbal caveats. So I think there's two stages we're trying to go through for this, and we're already working with them on bringing the caveats up in really sharp, bullet-pointed form, so they're inseparable from the graphic. They can't be lost down the bottom of some page somewhere. And the other thing I think eventually is to quantify some of these non-sampling errors. Now, why is this important in this area? Two things. First of all, we're doing empirical research, and our research suggests that if you can be confident about your uncertainty, then it doesn't reduce trust in the source. Confident uncertainty. What I call muscular uncertainty. I'm uncertain. What are you going to do about it? No, you've got to be, unapologetic uncertainty. And people are not stupid. They realize that you can't be sure about everything. And it doesn't reduce trust in the source. And the relevance of this to people here is that future official statistics are not going to be based on these big surveys. They're going to be based on data mining of routine data, administrative data, with all its problems, all its issues. That's where, since the Bean Review in this country, there'll be a huge amount more use of routine data. And so, I think these issues are very relevant. Okay, finally, yeah. Fairness. I'm not going to deal much with fairness. I'm just going to talk about this algorithm. Did anyone do this one? Heart age, when it came out last month? Heart age, yes, yeah. Any more heart age people? Yes, yeah, great. Okay. 2.9 million people did this algorithm in 3 days. And it was massively promoted. Basically, you can do it, don't do it now, but it's very easy to do. Just go on, click on there, and you fill in this stuff, including postcode. Uses postcode as a predictor. It does generally be considered as really racially biased if that was being used in other areas. Very dangerous to use. But anyway, it's being used here. Never mind. So postcode is a predictor, and it told me my heart was a bit older than I am, and told me to lose weight. Okay. So I thought, well, that's all right. Fair enough. I don't blame it. Okay. This heart age is a powerful tool. It's this idea of the effective age of your organ. You can go and find out your lung age, your brain age, and it's a generic idea. What is the age of a healthy person of the same risk or function as you do? So here's the graph. Basically, it says this is the trajectory, the risk trajectory as a healthy person gets older. It's always going to go up with age. Here you are, and your risk level is there. So actually what you've got is the risk level of a healthy person that age. So a very simple idea and very powerful. It's actually really just a transformation of the relative risk hazard ratio. It's a relative risk conclusion. Okay, and been phase 3 studies of this. Now, I'm interested in providing information rather than behavior change. This group weren't. They wanted to change behavior, and they found that when they randomized 3,000 people to get the heart age calculator, standard risk score, or control, the people with a heart age had more improvement in their risk score after a year. It was more motivating them. And lung age has been shown to be a motivating factor for people giving up smoking. Okay, so the heart age is a powerful emotional, communication. Now, what happened when this went out? I started getting emails from esteemed colleagues. What a load of crap. This is from a knighted maths professor, Sir something something. It just annoys you when it says I've raised risk factors when I have none. That's from a BBC producer. What utter bollocks this whole thing is. General practitioner. This is my favorite. I could have programmed that in my sleep, just a lot of random numbers designed to piss people off. Maths professor. Now, I thought, what have I done? What have I done? They were really angry. What irritated people so much? Nearly everyone has increased heart age. The healthy person has been set as very healthy. So 80% of people are going to be told they got increased heart age. Exercise is not in the equation. The thing that all these people were white, middle-aged, men who thought they were very fit, who exercised, and they put all their stuff in thinking, oh, it's going to tell me how good my heart is. And it told them all that they had an old heart. They were so angry. They felt it wasn't fair. Now, this is not a group normally that one has much sympathy for in terms of persecuted minorities, but it is indicative that fairness is not just racial bias. It can happen because you haven't included something that people really feel is important to them. It's not, exercise is not in there. So who is responsible for this algorithm anyway? Well, if they'd bothered to click through the website as to the credits and everything, they'd have found out it was us. I didn't own up. We took an existing a model to turn out the heart age calculations. It was very popular, it was very used, but we want to work on it now. It came from this database of 2.3 million people, so this is the BMJ paper. We used the coefficients, turned it into a heart age calculator by just using someone else's model. But now, I think we're going to go back and incorporate exercise into it, because I can't bear having these men sending abusive emails to me for the whole time. Okay, finally, final slide, conclusions. Conclusions. We need to demonstrate the trustworthiness of claims both by an algorithm and about an algorithm. That's the number one message from the whole talk. And part of that, especially the claims about it, come from, I think, a phased evaluation. These things should be subject to scientific rigor. I mean, it's a big thing to say they should be treated like pharmaceuticals, but certainly medical devices aren't that well regulated either, but certainly they should be treated seriously. There are statistical techniques about design. Experimental design is vital, about formally ranking algorithms, explanation, multiple forms and levels. And this is the thing I think is confident and reliable communication of uncertainty. Statisticians know a lot about this. We're obsessed with the uncertainty being as accurate as being as important as the estimate itself. And finally, there are many reasons why people might feel an algorithm is unfair. So thank you very much indeed.
We now have 10 minutes or so, 10 minutes, quarter of an hour for questions, and there are roving microphones, I'm told. I can't see in the Stygian darkness here, but somebody at the front here.
Oh, sorry. One thing, can I have the slides back? I didn't do my thanks. Oh, there. Right.
Okay, let's go.
Tim
Short questions, no speeches.
Is the microphone working? Tim Harford from.
Oh, that was your colleague, the second one.
I know. Tim Harford from the FT. David, this all sounds great. The question is whether you have in mind a code of practice, whether you have in mind some legal framework. And with drugs, there is a risk, and some people are worried about this, that there are all kinds of good drugs that just can't get through the regulatory process. Might we have good algorithms that can't get through the process? And are you worried about that?
Yeah, I mean, you got the multiple bodies interested in this, because there'll be Alan Turing Institute interested in this, where Adrian should reply on this. There's the Ada Lovelace Institute, there's this, Centre for Data Ethics and Innovation being set up, which is supposed to be advising on whether regulation is needed for these things. I don't know, I'm not going to say. I mean, many people have been suggesting certainly a code of practice among developers for this trustworthiness business, especially trustworthiness of the claims about the system. And I would think, absolute minimum of that.
But even if you were tempted, there are a lot of learned law articles on what are the legal issues if you were to try and regulate in this space. Yeah. Gentleman in the red. Orange, sorry.
Fantastic. Quick question, quick comment. Question first. Regarding the heart age data, exercise algorithm, given the non-existence of the exercise question in the first round, do most of you have a prior belief that exercise actually doesn't matter that much? It's more diet. That's the quick question. The quick comment is, I see so much overlap between what you've just said, discussed in the medical framework, and financial risk regulation, a la SR 11.7 from the US Fed.
Right. Okay, on the first thing, no, the suggestion is that exercise is an independent factor for improving cardiovascular health, and there's been a good meta-analysis recently that adjusts for the other factors that they've got there, and suggesting exercise does have an additional benefit on it. Exercise to definitely drop your heart age by a couple of years if you're with a reasonable benefit. It's non-linear. You can't just keep going. It levels off. But you get more than 20 minutes. You need more than 20 minutes a day. And I know nothing about the financial, but I can imagine that many of these aspects would also carry over. Really? Okay.
Good to look at.
Yeah. Right. Okay. Right.
Okay, lady in the front row here.
Thank you. The reaction to your Bank of England fan charts didn't encourage me to believe you about the people, about the effect of giving confident uncertainty. You gave a very good example of confident uncertainty, and certainly all the non-economists, and possibly some of the economists here, laughed. I wouldn't laugh at that chart. I think it's a very good chart, and you didn't laugh at that chart, but the majority here obviously doesn't agree with you. And also, your descriptions of predict didn't actually follow what you admired in your descriptions of the retinal study in AI, where there was an attempt to explain through the various pictures just why the AI found what it did find for various sorts of symptoms. Whereas the predict just said, if you do this, you will have a 3% greater chance or whatever. Why didn't you apply what you thought was good of that to the predict?
Very good questions. On the fan chart one, the fan charts, certainly financial journalists, won't include them in the news. They've been around for donkey's years and been copied by endless central banks, been shown to be extremely good and effective, and we are very happy to copy them. And we're doing, again, randomized trials, so people's interpretation of them seem to work very well. They're very effective. But certain people don't like them. And the other thing is that they also don't put in the point projection for the future deliberately to stop people anchoring on that. To just put the fan, not the central black line. So I think they're very powerful elements, but not everyone likes them. And we're going to see what happens with our migration stuff. The predict one, you're absolutely right. Because it's not a layered system like that, it's a simple scoring system. We have got the scores in there. You can find them to work out exactly how much each of those features was weighted in arriving at the risk. I've got to be completely honest, they're not very well explained at the moment. For example, we don't have what when putting this talk together, we hadn't got, when I said I'd give this talk, I thought, we will have all this fixed by now. This is now, I feel, having put this talk together and realized how much I liked the old stuff we did of the positive and negative features, the balance sheet, well, this increases your risk by this thing. We could do the same. We could do exactly the same with predict, about tumor size, things like that. And I think it's a real challenge. We should do it. we really should do. I think you can just sit down. You can take the coefficients and rearrange them so they're positive and negative, round them, of course, present them in a nice way, and I think it's a very good challenge. Now, we haven't done what I'm saying people should do, and I'm first to admit it.
Right. There's another question here over on the front.
I wondered why you chose to set the healthy heart mark for the how old is your heart thing. Why did you make your kind of reference person so healthy that 80% of people would fall below it?
Very good. No, I went back to our email correspondence because this was a clinical decision. This was, I said, well, should we just choose an average person? No. They wanted someone with low cholesterol, low blood pressure, or blood pressure 120 or something like that. So they wanted someone with optimum levels. So this was an aspirational target. So in fact, no, the choice of where that red line is almost a political decision by the people doing it about how many people do they want to fail this test in order to motivate them to improve their behavior. So that was a clinical decision to set it at a very healthy person, and thereby pissing huge numbers of people off. And if I thought I got a lot of stick, there's nothing to what some of the doctors got.
Yeah, the knighted maths professors are sitting at the back. Go to that. Yes, there, straight front. Yeah.
Just one question about fairness. I mean, how do you decide, or do you have any ideas about how one deals with the fact that a predictor might be ethically questionable, but might be a very, very powerful predictor? So I'm just thinking, for instance, neighbourhood. So if you take neighbourhood, it's a very interesting one because neighbourhood does appear in a lot of criminal risk algorithms. And I was very surprised once when a social scientist pointed out to me that it's actually a modifiable risk factor because it's a way of trying to get policymakers to improve the quality of the neighbourhood. So I never thought about it like that. But you can see that actually people can even see something like neighbourhood, which looks very static, as actually something which has potential to change and influence policy.
Yeah, it's a very important issue, and the point is that you can have predictors that are very good, but they tend to be associational predictions. They're not the direct causal path. They're things that tell you they're surrogates for something else, and they can work very well indeed. But it has to be another decision about whether it's ethical to include them. And exactly the same thing happens if you get looking for a life insurance policy. There are all sorts of factors about you. Not you personally, maybe, but which a company could ask that they could use to make their insurance much more effective. But for example, for genetics, they're only allowed to ask about Huntington's disease. It's the only one you're allowed to ask about. You're not allowed to ask about race, but you can ask about family history, which can give it away. There's all sorts of things that there is regulation about can be asked, and so it's a totally different issue about producing something that can predict well, and whether it's a fair thing to use in an algorithm. And Compass, of course, uses all sorts of background information, and we don't know what's being weighted at all.
Okay, one final question. The hand is up over there. Then we shall move to further questions, but outside the lecture theatre. Okay.
Obviously, I understand, as a result of the audience and the nature of the discussion, that it was addressed mainly towards practitioners. But I was wondering, given that a lot of what you said... Also, sorry, by the way, fantastic talk. A lot of what you said was directed towards practitioners, but I wonder definitely whether or not you could expand on kind of what principles, questions, non-practitioners who may be asked to be used to use algorithms, what they should keep in mind, whether it's in the form of communication or applying what an algorithm says.
Yeah, I think it's very important about almost what questions to ask of it. If you're a punter, consumer, what question to ask of it. And I think it's these lists that people are making, and which I've been slightly adding to, are terribly important. You want to be able to have an explanation of why a particular conclusion has been drawn about you. So you want that interpretability. Yeah, you want to be able to check, if necessary, its trustworthiness. So you want to be able to check it's working. Not necessarily all the time, but if you want to, you should be able to sat down and have it explained why the conclusion was drawn, what would have had to change, in order for you to get a different decision, and so on. And I think these are reasonable things for consumers to ask. And under GDPR, because it hasn't been fully established yet quite how much of a right that is. So I think that these are. I hope I'm talking to both audiences, the people developing them and the consumers, because the consumers should be demanding. They should be pushing back. They shouldn't just be accepting stuff that's being done to them as passive elements. They should be mobilizing to ask these questions of systems, no matter how nice they look. Because again, over trust. Our problem with Predict is that it looks too good now. Everyone loves the damn thing. It's great. It's good, but it's not that good. There's lots of features that aren't in there, and all stuff like that. It's okay. It's good. It gives a ballpark figure, and I think it's very useful. But it's not. People can trust these things too much. And I think that's the element. So I think trustworthy communication is hugely connected up with actually giving the limitations, acknowledging the limitation, making sure they're not lost, like we're trying to do in the migration, et cetera, et cetera. That's why I think these things like the Bank of England are really good lessons to try to learn from.
Okay, we are now going to move outside. Can we thank David for a fantastic lesson?
Thank you very much. Thank you.